let's get started with Chapter 2. So Chapter 2 is all on chemistry, focusing on the terms, reactions, molecules, atom stuff that you'll need for not only AP1 but also AP2. Skip. There we go. Okay, so structure of an atom. So when we talk about an atom, we focus on what's called the planetary model. So like your central portion of the atom would be like a sun, and then these other little small parts that orbit around are like the planet. So like just like our solar system. So what's making up our sun, or the center part or nucleus of our atom, is the center of the atom is the nucleus. It's made up of protons and neutrons. Protons are positively charged and have an atomic mass unit of 1. Neutrons are neutrally charged, so it has no charge on there, and it has an atomic mass unit of 1. So this is where you get the weight or mass of your atom. So you add up the number of protons in your element and the number of neutrons. Our last little bit, our little orbiting planets, are our electrons. So for our electrons, they are negatively charged. So our negatively charged electrons and positively charged protons are going to essentially, for the most part, balance each other, unless they are sometimes making a bond with other elements, and so they'll either lose a proton, lose an electron. With bonds, it's with electrons. Sometimes the element gets damaged. You actually can break up the nucleus, but that's in more of your nuclear physics and all that jazz. Okay, so the ones that we really want to focus on for the electrons are the valence electrons. So these are the ones that orbit in the outermost shell. So if I look up to my little planetary model at the top, we have our protons and neutrons, and then we have orbiting shells of electrons. So in this last shell of this molecule, we have one single solitary electron. So that atom is going to have one electron that is on the outside that's going to form a bond. And with that type of atom, atoms don't like to be unhappy. There's actually a certain number that they like to have. So this one most likely will end up getting rid of that electron to make a bond. Okay. So structure of an atom, just kind of reviewing. We have our nucleus, which is the mass of the atom, which is the protons plus our neutrons. Then on the outside, we have our electrons, which are negatively charged. They orbit around, and the last outer shell of orbiting electrons likes to have 8 electrons in these outermost orbit, so that makes that one happy. So a lot of times when it comes to making bonds and how many bonds it can make, depends on the number of those electrons. Okay, so just going over mass. So with our carbon atom, we have 6 protons, 6 neutrons, so our atomic mass is 12. Good job. For nitrogen, so 7 protons, 7 neutrons, so it has an atomic mass of 14. And last one, just as a good last example, here we have a difference in number between the protons and neutrons, but we still add both of them together to get the atomic mass. So we have 11 protons, 12 neutrons to make 23 as the atomic mass. So if you look on a periodic table of elements, you'll actually see where these are on your chart. You'll have the atomic mass. It's slightly off because in a sample of a set of atoms, you'll have some that might have an extra proton, or not extra proton, extra neutron, and that extra neutron is going to cause it to have a slightly different weight, so a little bit heavier, and so that's why the numbers are a little bit off. But for atomic number, it's based on the number of protons. Okay, so with our atoms, They can give away electrons or they can receive electrons. And when they do that, it's called ionization, so transfer of electrons. So when an atom gets rid of one or adds an electron, it becomes an ion, so it has a charged particle. So instead of having an even number of protons and electrons, when it gets rid of this extra one that it doesn't like on the outside shell, so here in the second shell it has 8 electrons, so that means it will be nice and happy, so it will gladly get rid of this one. Here, this chlorine will gladly accept it, so its outermost shell of electrons is 7, so it will gladly take that last one so that it can have a valence shell of 8. So sodium and chlorine will very often pair with each other. Same thing with other elements. It's based on that valence shell. So it moves over. So when this process happens, this ionization, you end up with anions and cations. So an anion is an atom that gains an electron, so it is negatively charged. A cation is one that loses an electron, so it's now positively charged. So again, instead of having a balance, we have 11 positively charged protons, 10 negatively charged electrons. So we have this one extra charge on the protons. So we have our sodium ion with a positive charge of 1. You can have some that lose or gain multiple electrons, and that's going to affect that charge number. So for example, calcium will lose 2 electrons, and so it will have a charge of +2. So atoms that do this, molecules that do this with their ionization, that also creates a bond. We'll talk about that later. Those types of molecules are called electrolytes. So when they get into water, they'll ionize so that they break apart into its positive and negative ions. So for example, going back to our sodium chloride, so this is actually bonded together. So we had our shift over of our electron. You put that in water, it's going to break apart. So instead of these two balancing each other in charge and being a nice happy molecule, it gets in water, and I'll show you how water does that later. So when you have all these positive and negative ions floating around, you're able to conduct electrical currents. So for example, again, going back to sodium chloride. Sodium chloride is salt. What's in a pickle? Salt. So if you've ever seen that cute little experiment where they attach the wires to both ends of the pickle and you can see the pickle light up, it's because the electrolytes that are in the salts that are in the pickle allow for that electricity current to go through there, and you actually can see that light being produced. So we'll see the function of electrolytes in multiple areas for AP1 and AP2, and AP1 will get into dealing with muscle stimulation as well as nerve stimulation and how that's able to work. So we need those electrolytes in order to do that. So here's some common ones. You won't have to actually know them from my class, but these are just some of the ones that you see a lot of times, especially if you have your Gatorade or whatever, and you'll see these same ones that are in there, or Powerade, whatever. So these are common ones that are in our body that our body needs a lot of. Okay. So with our atoms, they do create molecules, so our next level of hierarchy of complexity. And we're actually able to denote what they are based on the letter that represents the atom, and then showing these little lines where the bonds are between them. So they can have the exact same molecular formula, but depending on how they bond, you can create ethanol, which you can drink, ethyl ether, which will kill you. Okay, so with our bonds, there's 4 different ways to make the bonds, and that's how we hold our atoms together. So the first type is ionic bond, like we showed earlier with the sodium chloride, where electrons move. So one is going to go to another atom. Next type is a covalent bond with shared electrons, hydrogen bonds, and the last one, which is called van der Waals forces. So for an ionic bond, here we have sodium and chlorine up the top, and we have our ionization process, our electron, so unhappy by itself. It goes over to chlorine into a nice 8-valent shell of electrons, so it's nice and happy. This creates a bond between these two atoms. This type of bond is easily broken by water. So again, in this case, chloride has the sole custody of the electron. So it's going to stay around that nucleus and orbit there. It's not going to go back to sodium because everyone is nice and happy. Next type of bond is your covalent bond. So you can have a single covalent bond, a double covalent bond, or even a triple one. So in this case, the electrons are shared between both atoms. So they're going to orbit around the nuclei of both atoms. So they kind of go in a cloud type of motion, orbiting around both of them. So it just makes a bigger space where they normally are. You can also do it with a double bond. So here we have carbon dioxide molecule, so carbon in the center, double bonded with oxygen, double bonded with another oxygen. So carbon, it only has 4 electrons in its outer valence shell, so it likes to have 4 different bonds with other atoms. So this is the easy way. Oops. New one. There we go. So we have 1, 2 bonds there, 1, 2 bonds there. So in a double covalent bond, they're going to orbit around the ones that they're sharing. So it's not like this set here is going to orbit all the way over here. It just only orbits around the 2 neutrons that are 2 nuclei that are sharing it. And on this side, these will only orbit, the ones that they're being shared are going to only orbit around in this case, the oxygen and carbon atom creating that bond there. Okay, so with our covalent bonds, depending on the mass of the atom, so the nuclei more specifically, you're going to have a difference in how the electrons orbit. So for this covalent bond, we have 2 carbon atoms. Carbons have the same amount of mass, so they're going to have the same type of gravity-like attraction. So our electrons are going to evenly orbit around both carbon atoms. For this bond between the oxygen and the hydrogen is really small. Oxygen, a lot larger. So in this case, the electrons are going to spend more time around the oxygen. This makes the oxygen on this molecule a little bit more negative because the electrons are spending more time here and the electrons are negatively charged. So in this case, your hydrogen ends up being a little bit more positively charged. And this is what helps when it comes to water molecules and how they bond together. So we have our water molecule with our oxygen with more electrons hanging around it, so it's more negatively charged on that end, more positively charged on our 2 hydrogen atoms. So in this case, the negative charge oxygen likes to hang out with our positively charged hydrogen, and that creates a very weak bond called a hydrogen bond. So these bonds is what keeps essentially water hanging on to itself. So when you are going from a liquid to a gas and water, it does take some energy to break that attraction so that your liquid water can become steam or gas phase. This is also how our large molecules that we'll talk about later, chapter 3 and 4, DNA and proteins, another way how they're able to keep their shape is with these weak hydrogen bonds. And the last bond is a van der Waals forces. This comes into play when you are folding up a protein into its correct shape. So you go from a straight protein with all of its little building blocks, so like a straight line, and then it folds up into whatever functional shape it's supposed to have. Oops. So in that functional shape, those bonds help to keep it in that shape, and that's actually very important for that protein to do its job. So that's the end of the first video for chapter 2. I try to keep these under 15 minutes or close to it. So the next one's going to start here at 2.2 for water and mixtures.